Right now, as you read these words, there exists a world orbiting another star. Not a theoretical world, not a statistical probability buried in telescope data. A specific planet with a mass, an orbit, a surface of some kind, rock or ice or something. Stranger circling a dim red sun, 4.2 light-years from where you are sitting. Astronomers gave it a name in 2016, Proxima b. And in the long, quiet history of humanity looking upward and wondering whether anything exists out there beyond the dark, the discovery of this world represents perhaps the single most important moment since Galileo first turned a lens toward the sky. 4.2 light-years. When you first hear that number, something in the mind reaches for familiarity. 4.2. It sounds manageable, approachable, the kind of number you encounter in daily life, the distance to the nearest coffee shop, the hours in a short flight, the weight of a bag of flour. We hear nearest star, and the brain, conditioned by a lifetime of solvable distances, whispers, surely that is achievable. Surely that is merely a matter of time and will and the right machine. That whisper is lying to you. It is the most seductive lie in all of science because it comes dressed in the clothing of reason. 4.2 is a small number. Light years are simply a unit of measurement. Units can be converted, distances can be crossed, problems can be solved. The mind assembles these premises and arrives at a conclusion that feels logical, and the conclusion is catastrophically wrong. Because a light year is not a distance that belongs to human experience. It is not a distance that belongs to human history. It is barely a distance that belongs to human imagination, and imagination is the most expansive faculty we possess. A single light year is the distance light travels in one full year. Light moving at approximately 300,000 kilometers every single second covers 9.5 trillion kilometers in the span of 12 months. Multiply that by 4.2. The result is roughly 40 trillion kilometers of empty, lightless, airless void, separating you from the only known world outside our solar system that might possess conditions permitting liquid water on its surface. 40 trillion kilometers. Your mind cannot hold that number. No human mind can. We are creatures who evolved to navigate savannas and coastlines, to judge the distance to prey, and to shelter to plan journeys measured in days of walking. The neural architecture that allows you to read these words, to feel the weight of a concept, to be moved by beauty, that architecture was not built to comprehend scales of this magnitude. When we encounter such numbers, we perform a kind of intellectual gesture toward understanding without ever truly grasping them. We say the words, we write the figures, we nod. But the visceral cellular comprehension that accompanies knowing the distance to the kitchen or the drive to a friend's house that never comes. So let us try to build it from smaller pieces. Imagine the entire distance from the Earth to the Sun, 150 million kilometers, a journey that would take a commercial airliner nearly 19 years of continuous flight compressed into a single centimeter. A centimeter, the width of your thumbnail. At that scale, the distance to Neptune, the farthest planet in our solar system, would stretch roughly 60 centimeters. You could hold the entire scope of everything humanity has ever explored with robotic spacecraft in the span of your two outstretched arms. Proxima Centauri at that same scale sits 4.2 kilometers away. Not 4.2 centimeters, not 4.2 meters, 4.2 kilometers. The distance to a different neighborhood, a different part of town somewhere, requiring a vehicle and a map. Everything our telescopes have photographed up close, every world our probes have orbited or landed upon, every piece of the cosmos we have touched with instruments, all of it fits between your hands. And the nearest other star requires a journey that at this scale would take you out of your home, down roads past other buildings into territory your feet have never walked, and that is merely the nearest one. The Milky Way galaxy stretches 100,000 light-years across. If Proxima Centauri is a different neighborhood 4 kilometers away, the far edge of our galaxy sits at a distance comparable to circumnavigating the Earth twice. And our galaxy is one of an estimated 2 trillion galaxies in the observable universe, each containing hundreds of billions of stars. The mind does not collapse under this information. It simply goes quiet. There are no words adequate to the task of containing it. But we must return to 4.2, because 4.2 is in the truest sense all that matters right now. In 2016, a team of astronomers using the HARP spectrograph at the European Southern Observatory in Chile announced they had detected something extraordinary. A subtle rhythmic wobble in the motion of Proxima Centauri, our nearest stellar neighbor, a dim red dwarf, visible only through telescopes hanging 11 degrees from the southern celestial pole. The wobble was small, almost impossibly small, a shift in the star's radial velocity of barely 1.5 meters per second. But it was real, and it was periodic, repeating every 11.2 days with the clockwork regularity that could only mean one thing. Something was pulling on that star, something with mass, something in orbit. They named it Proxima b, and within days of the announcement, the question that had shaped 3 decades of exoplanet science, are there worlds around other stars that could support life, acquired a new and specific gravity? Because Proxima b orbits within its star's habitable zone, at a distance of roughly 7.5 million kilometers from Proxima Centauri, far closer than Mercury orbits our own sun, but appropriate, given how much cooler and dimmer the red dwarf burns the planet receives, approximately 65% of the stellar energy Earth receives. Enough in principle for liquid water to exist on a rocky surface. Enough in the language of planetary science to warrant the word habitable as a genuine possibility rather than a polite fiction. The planet's mass is estimated at no less than 1.3 times Earth's. Rocky most likely. Solid, a surface of some kind. For the first time in human history, we had a name, an orbit, a mass, and a location for a world that might in some form, under some conditions, harbor something resembling life. And it orbits a star visible just barely to the naked eye on a clear night in the southern hemisphere. The discovery changed everything about the question of interstellar travel. Before Proxima b, discussions of reaching other stars were abstract exercises, thought experiments dressed in engineering language, motivated more by philosophical curiosity than any concrete destination. After Proxima b, there was an address, a specific place, a world with properties we could begin to measure and debate and imagine standing on. The universe had placed the most tantalizing possible target at the closest possible location. And then the physics reminded us what 4.2 light-years actually means. If you wanted to travel to Proxima b within a single human lifetime, not in comfort, not safely merely arrive within roughly 80 years of departure, your spacecraft would need to sustain a velocity of approximately 5% the speed, kind of light. That translates to roughly 15,000 kilometers per second, every second, for 8 decades. To understand how far that is from anything we have achieved, consider that the Parker Solar Probe, the fastest human-made object ever built, reaches speeds close to 200,000 kilometers per hour during its closest approaches to the Sun. That is approximately 55 kilometers per second. 15,000 kilometers per second is 270 times faster. Not 20% faster, not twice as fast, 270 times faster than the fastest object humanity has ever constructed, and that would still require a full human lifetime to make the journey. If you wanted to arrive in 20 years, a timeline ambitious but not absurd for mission planning purposes, you would need to travel at roughly 20% the speed of light, 60,000 kilometers per second, more than 1,000 times faster than our current speed record. That is the problem. Not the engineering, not the materials, not the funding. The fundamental physical, mathematical reality that the universe has arranged itself so that the distances between stars require velocities no current technology can approach, and the energy required to reach such velocities exceeds anything our civilization has ever generated for a single purpose. This is not pessimism. It is not a failure of imagination. It is the universe operating according to its own rules, indifferent to our curiosity, or our longing, or the beauty of the question. But the question remains beautiful, and the attempt to answer it, the history of every propulsion concept, every laser array design, every gram-scale spacecraft imagined and debated and partially built, that attempt tells us something essential about what kind of species we agrare. Whether we deserve the stars is a question only the stars can answer. But whether we will keep reaching for them, that answer at least seems clear. If you find meaning in journeys that reframe everything you thought you understood about distance and time and human ambition, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow, and it means these explorations can continue. Make yourself comfortable. Clear your mind of the immediate and the small. Let's begin. The number 4.2 has a kind of poetry to it. Small enough to speak without hesitation, precise enough to feel scientific. It sits in the mouth without difficulty, 4.2. And this is the first trap the universe sets for anyone who begins thinking seriously about interstellar travel. Not ignorance, not lack of data, but the seductive smallness of the number itself. 4.2 light years. We have been using the word light year for so long in so many contexts that it has lost its capacity to shock. It appears in science, journalism, and documentary narration, and casual conversation with the ease of a familiar word. We hear it and we think, yes, a unit of astronomical distance, large. We move on. The word has been domesticated. Let us make it wild again. Right now, at this precise moment, light is leaving the surface of the sun. It is moving at 299,792 kilometers per second. It is moving so fast that in the time it takes your heart to complete one beat, that light has traveled roughly 300,000 kilometers. It will reach Earth in 8 minutes and 20 seconds. It will reach Neptune, the outermost planet, in approximately 4 hours. It will pass Voyager 1, our most distant probe, currently more than 24 billion kilometers from Earth, after nearly 5 decades of travel in roughly 22 hours. And that light will not reach Proxima Centauri for 4 years and 2 months. 4 years and 2 months of travel at the fastest speed physically possible in this universe. And this is not 4 years of crossing empty space as we experience emptiness in daily life. This is 4 years of traversing a void so absolute that the human senses have no vocabulary for it. No air, no warmth, no sound, no gradient of pressure or texture or resistance. A darkness uninterrupted by anything except occasionally the passage of a single atom of hydrogen drifting alone through billions of cubic kilometers of absolute nothing. This is what lies between us and Proxima b. Now consider what we have built to cross it. Voyager 1 was launched from Cape Canaveral on September 5, 1977. It was built to study Jupiter and Saturn, to photograph their moons in unprecedented detail, to pass through the outer solar system and gather data that no instrument had gathered before. It succeeded beyond almost every expectation. The images it returned of Jupiter's turbulent atmosphere, of the volcanic surface of Io, of the intricate geometry of Saturn's rings, these images changed our understanding of our own solar system irrevocably. And then Voyager kept going. It has been traveling for nearly 5 decades. It crossed the boundary of the heliosphere, the bubble of charged particles blown outward by the sun, in August of 2012, becoming the first human-made object to enter true interstellar space. This was celebrated as one of the great achievements in the history of exploration, and rightly so. Voyager 1 became our first ambassador to the space between stars. Today it sits approximately 24 billion kilometers from Earth. At its current velocity of roughly 17 kilometers per second, Voyager 1 would require approximately 73,000 years to reach Proxima Centauri, assuming it were headed in the right direction, which it is not. The spacecraft is moving toward the constellation Ophiuchus. It will not make a close approach to any star for tens of thousands of years. 73,000 years. The agricultural revolution began approximately 10,000 years ago. Every recorded human civilization, every written language, every city and empire and philosophical tradition and scientific discovery in human history has unfolded within the last 10,000 years. Voyager 1 at its current speed would require 7 times that span of time to cross the distance to our nearest neighbor. Your great-grandchildren will live and die. Their great-grandchildren will live and die. 60,000 generations of human beings will be born and grow old and return to the Earth. Civilizations will rise and collapse into silence. Languages will emerge and become extinct, and Voyager 1 will still be traveling, still crossing the void, still not there. This is the baseline. This is what we have. The gap between this baseline and what interstellar travel requires is not a gap of degree, it is a gap of kind. It is the difference between a canoe and a transcontinental railway, except the canoe took 5 decades to build and represents the pinnacle of our current capability, and the railway does not yet exist even in blueprint form. But before we examine what that railway might look like, we need to understand why building it is so extraordinarily, almost perversely difficult. And to understand that, we need to talk about an equation. In 1903, a Russian schoolteacher and self-taught rocket theorist named Konstantin Tsiolkovsky published a paper that would determine the fate of every spacecraft humanity would ever build. Tsiolkovsky was a remarkable figure, partially deaf since childhood, largely self-educated, working in isolation in a small town, far from the scientific centers of Europe, yet possessed of a mathematical intuition that placed him generations ahead of his contemporaries. He had been thinking about rocketry and space travel for decades by the time he committed his central insight to paper. The equation he derived appears deceptively simple. The change in velocity a rocket can achieve depends on 2 things: the speed at which it expels its propellant and the ratio of the rocket's initial mass, including all its fuel, to its final mass after the fuel is gone. The relationship between these quantities is logarithmic. As your desired velocity increases, the required fuel mass does not increase proportionally. It grows exponentially. This is the rocket equation, and, for interstellar travel, it is effectively a death sentence for conventional propulsion. Consider what this means in practice. A chemical rocket, the kind that has carried every human being beyond Earth's atmosphere, the kind that powered the Saturn V to the Moon, the kind sitting in every active space program on Earth today, expels its propellant at approximately 4 to 5 kilometers per second. This is the exhaust velocity, and through Tsiolkovsky's equation, that exhaust velocity acts as a fundamental ceiling on what is achievable. To accelerate a spacecraft to 1% of the speed of light, 3,000 kilometers per second, still barely a crawl in interstellar terms, still requiring over 400 years to reach Proxima b using chemical propulsion, you would need a fuel-to-payload mass ratio, in the ratio, neighborhood of 10 to the power of 280. That number is not a large number. It is not an astronomically large number. It is a number so far beyond the count of atoms in the observable universe that no physical object could ever embody it. Every atom of matter in the cosmos, if converted entirely to rocket fuel, would not be sufficient, not even close, by many orders of magnitude, not close. Chemical propulsion does not need to be improved to enable interstellar travel. It needs to be abandoned entirely. The physics of combustion chemistry, the energy available per unit mass in molecular bonds, places a hard ceiling on exhaust velocity that no engineering advancement can raise. You cannot burn hydrocarbons fast enough to reach the stars. The universe has set a limit, and that limit was set long before Tsiolkovsky wrote it down. This is not a temporary engineering problem, it is a fundamental physical constraint, and it is the first wall humanity must climb before any serious conversation about reaching Proxima b can begin. There is a spacecraft currently orbiting the asteroid belt, or rather there was. Dawn, launched by NASA in September of 2007, became the first mission in history to orbit 2 separate extraterrestrial bodies, the asteroid Vesta and the dwarf planet Ceres. It did this not by carrying enormous quantities of chemical fuel, but by using something far more elegant, far more efficient, and in the context of interstellar ambition, far more instructive about the nature of the problem we face. Dawn was powered by ion propulsion. The principle behind an ion drive is straightforward enough to state in a single sentence, yet the engineering required to make it work in deep space took decades to perfect. Xenon gas, heavy, chemically inert, easy to store, is fed into a chamber where electrons strip away from individual atoms, creating positively charged ions. These ions are then accelerated by an electric field and expelled through a grid at the rear of the spacecraft at velocities approaching 40 kilometers per second, nearly 10 times faster than the exhaust from the best chemical rocket engines ever built. 10 times faster. That matters enormously, because exhaust velocity feeds directly into Tsiolkovsky's equation. A higher exhaust velocity means a more favorable fuel-to-payload ratio. A more favorable ratio means less propellant needed for the same velocity change. Less propellant means a lighter spacecraft. A lighter spacecraft means more of the launched mass is actually useful payload rather than dead weight being lugged through the void. The cascade of benefits from improving exhaust velocity is real and significant. But there is a cost, a severe one. Ion drives produce extraordinarily weak thrust. Dawn's 3 ion engines operating simultaneously at full power generated a combined thrust of approximately 91 thousandths of a newton. To give that number some physical meaning, it is roughly equivalent to the force exerted by a single sheet of paper resting on your palm, less than the weight of a postage stamp. If you placed Dawn's ion engines on a table and ran them at full power, you would not be able to feel the thrust against your fingertip. In the vacuum of space, with no friction and no gravity to fight, this gentle pressure accumulates. Over days it becomes noticeable. Over weeks it becomes significant. Over months and years it propels a spacecraft across the solar system on trajectories impossible for chemical rockets. Dawn spent more than 3 years thrusting almost continuously, gradually spiraling through the inner solar system before entering orbit around Vesta. The mission was a genuine triumph of patient, efficient propulsion. Yet for interstellar purposes, ion propulsion's limitations become immediately apparent when the mathematics are applied. The exhaust velocity of an ion drive, impressive as it is relative to chemical rockets, remains a tiny fraction of the speed of light. 40 kilometers per second sounds fast. It is fast by every human standard, but the speed of light is approximately 300,000 kilometers per second. Dawn's ion exhaust moves at roughly 1/7,000th of that velocity. And once again, Tsiolkovsky's equation transforms this limitation into crushing numbers. To reach even 1% of light speed using ion propulsion, you would still require a fuel-to-payload ratio in the billions. To reach the 5 or 10% necessary for a mission completing within a human lifetime, the numbers become grotesque. At ion drive speeds, a spacecraft launched toward Proxima Centauri today would arrive in approximately 17,000 years, better than the 73,000 years Voyager would require. Genuinely better by a factor of more than 4. But 17,000 years is not a mission, it is a geological epoch. It is the span of time separating us from the construction of the first megalithic monuments. Every language spoken on Earth today would be unrecognizable to the descendants of the engineers who built the spacecraft. The very concept of the nation-states funding such a mission would be historical footnote. The spacecraft would arrive at Proxima b in a future so remote that we can form no meaningful connection to it. Ion propulsion expanded our reach within the solar system. It did not bring the stars closer. The next step up the ladder of propulsion technology involves the atom itself. Nuclear thermal rockets operate on a principle that seems almost obvious in retrospect. Chemical rockets burn fuel to generate heat, and that heat drives exhaust gases out the back. The limitation is that chemical reactions can only generate so much heat bounded by the energy stored in molecular bonds. But nuclear fission reactions release energy orders of magnitude greater per unit mass. What if, instead of burning fuel, you used a nuclear reactor to heat a propellant to temperatures far beyond what any combustion process could achieve? The answer, worked out in extraordinary detail by American engineers during the 1960s and early 70s under a program called NERVA Nuclear Engine for Rocket Vehicle Application, is that you can roughly double the exhaust velocity of a chemical rocket. Where the best hydrogen-oxygen engines achieve specific impulses around 450 seconds, nuclear thermal designs reached specific impulses of 800 to 900 seconds in ground tests. The Phoebus 2A reactor, tested in 1968, generated over 4,000 megawatts of thermal power and demonstrated thrust approaching 112,000 newtons. These were not theoretical calculations. These were real engines tested in the Nevada desert, producing real thrust from real nuclear reactions. The NERVA program proved that nuclear thermal propulsion was not science fiction, it was engineering. Solvable, buildable, testable engineering. Congress cancelled the program in 1973, not because it failed, but because the political will for deep space human missions had evaporated after Apollo, and without a destination, a superior rocket engine had no constituency. The hardware was mothballed, the engineers dispersed, the knowledge partially preserved in classified reports and the memories of men who are now elderly or gone. In recent years, interest has resurged. NASA's Space Technology Mission Directorate has funded new nuclear thermal propulsion research. Proposals have been submitted, budgets debated, timelines sketched. The technology remains viable. For missions to Mars, nuclear thermal propulsion could reduce transit times from 9 months to 4 or 5, a difference that matters enormously for crew, health, and mission cost. For the outer solar system, the efficiency gains would enable entirely new categories of science. But for interstellar travel, nuclear thermal propulsion suffers from the same fundamental limitation as everything that came before it. The exhaust velocity has been doubled, but doubled is not enough, not nearly enough. The required exhaust velocity for a practical interstellar mission is not twice what a chemical rocket achieves. It is thousands of times greater. Doubling from 4 kilometers per second to 8 kilometers per second moves the transit time to Proxima b from geological epochs to merely very long geological epochs. The arithmetic is merciless. At nuclear thermal speeds, a spacecraft would reach Proxima b in approximately 12,000 years, 5,000 years better than ion propulsion. Still an abyss between ambition and reality. Then there is Franklin Chang Diaz. Born in Costa Rica, trained as a physicist at MIT, selected as a NASA astronaut in 1980, and ultimately the holder of the record for most space flights. 7 missions on the space shuttle. Chang Diaz spent his career pursuing a propulsion concept that seemed, when he first began, advocating for it seriously, like the sort of idea that lived in the gap between serious science and wishful thinking. He called it Voyager, the Variable Specific Impulse Magnetoplasma Rocket. The name is a mouthful, but the concept is worth understanding in detail, because Voyager represents one of the most sophisticated plasma propulsion systems ever brought from theory to hardware. Where an ion drive accelerates individual ions through an electric field, Voyager takes a fundamentally different approach. Radio waves, the same phenomenon that carries your wireless signals, are used to heat a propellant gas, typically argon or hydrogen, to temperatures exceeding 200,000 degrees Celsius. At these temperatures, the gas becomes a plasma, a state of matter in which electrons have been stripped entirely from atomic nuclei, creating a soup of charged particles with properties unlike any solid liquid or conventional gas. Powerful superconducting magnets then confine this superheated plasma, shaping and accelerating it into a directed exhaust beam. The key innovation is in the name itself, variable specific impulse. Unlike most rocket engines which operate at a fixed exhaust velocity, Voyager can be adjusted in real time. In one configuration, the engine produces relatively high thrust at lower exhaust velocities, useful for rapid maneuvering or fighting against gravity near a planet. In another configuration, it sacrifices thrust for extreme exhaust efficiency, generating velocities that approach 50 kilometers per second or beyond. A spacecraft equipped with Voyager could theoretically operate in the high-thrust mode when it needs to change orbits quickly, then switch to high-efficiency mode for long interplanetary cruise phases. Chang Diaz founded Ad Astra Rocket Company in 2005 to develop Voyager into a flight-ready system. The VX-200 engine tested at Ad Astra's facility in Texas demonstrated sustained plasma generation and thrust production at 200 kilowatts of input power. The test results matched theoretical predictions closely enough to validate the fundamental design. Ground-based firing tests have run continuously for hundreds of hours, demonstrating the durability that long-duration space missions require. The projected performance is genuinely impressive by any previous standard. With sufficient power, and this qualification will matter enormously in a moment, Voyager could theoretically reduce a transit from Earth to Mars to as little as 39 days. The 9-month journey that currently defines the outer boundary of human deep space capability compressed into a single month of flight. For a crewed Mars mission, this difference is not merely convenient, it is potentially mission-enabling, reducing radiation exposure by a factor of 8, drastically changing the psychological calculus of confinement, and opening mission architectures that chemical propulsion simply cannot support. But the qualification with sufficient power is not a minor footnote. It is the central constraint around which everything else orbits. Voyager is an electric propulsion system. Unlike nuclear thermal rockets, which generate their own heat directly from fission reactions, Voyager requires an external source of electrical power to generate the radio waves that heat its plasma. At the power levels necessary to produce meaningful thrust, this means a nuclear reactor aboard the spacecraft. A 200 kilowatt Voyager demonstration is modest in power terms. Scaling to the megawatt level systems required for the fastest Mars transits demands reactors that do not yet exist in space-qualified form, adding not just mass but complexity, thermal management challenges, and radiation shielding requirements. Every kilogram of reactor, every kilogram of radiator panels dissipating waste, heat, every kilogram of shielding protecting crew and electronics from the reactor's output, all of it must be accelerated along with the payload. The efficiency gains of Voyager begin to erode as the supporting infrastructure grows heavier. The mathematics remains relentlessly honest. You cannot carry a power plant to the stars for free. And when the transit time calculations are made for Voyager operating at achievable power levels, the answer arrives with the same blunt finality as every propulsion system before it. Approximately 1,200 years to reach Proxima Centauri. Better than nuclear thermal. Better by an order of magnitude over ion drives. Genuinely better in ways that matter for exploring our solar system, but still more than 1,000 years of travel time for a destination we want to reach in decades. Chang Diaz remains one of the most thoughtful advocates for plasma propulsion, and his work has real value for the future of space exploration within our solar system. The intellectual honesty of the Voyager program is admirable. The team makes no claims beyond what the physics and the tested hardware support. Voyager is a serious technology being developed by serious people. It will almost certainly play a role in humanity's future in space. That role just doesn't include reaching Proxima b. 1,200 years, 1,200 years, the lifetime of the Holy Roman Empire, twice the span separating us from the signing of Magna Carta. Voyager, the most sophisticated plasma propulsion system ever built, carrying the work of a NASA astronaut with 7 spaceflights and a physics doctorate from MIT, cannot bridge the gap. This is not a failure of the technology. It is not a failure of the engineer. It is the universe again operating on its own terms. But something important has emerged from this progression. From chemical to ion to nuclear thermal to plasma. Each step upward has improved exhaust velocity, reduced transit times, opened new regimes of capability. The curve is moving in the right direction. The problem is that the destination interstellar travel within human-relevant timescales requires not another step up this curve, but a leap of entirely different character. What if instead of carrying propellant at all, you carried nothing? What if the force that pushes you comes not from within the spacecraft, but from something that stays behind? This is the insight that changes everything, and it begins with a sail, not a metaphor, not a poetic gesture toward the seafaring tradition of exploration, an actual sail, a physical membrane stretched taut against the void, catching something and being pushed by it. Johannes Kepler, writing in 1610, noticed that comet tails always point away from the sun, regardless of the direction of the comet's travel. He speculated that some kind of emanation from the sun was pushing the tail material outward. He was right. The sun continuously releases a stream of photons, particles of light, and those photons, despite having no mass, carry momentum. When they strike a surface, they transfer that momentum. A reflective surface, like a mirror, experiences twice the push of an absorbing surface because the photon bounces back and imparts its momentum twice. The force is extraordinarily small. At Earth's distance from the sun, sunlight exerts a pressure of approximately 9 micronewtons per square meter, 9 millionths of a newton across an entire square meter of perfectly reflective surface. To put this in tactile terms, if you covered your outstretched hand, perhaps 150 square centimeters, with a perfect mirror and held it in sunlight. The total solar radiation pressure pushing against it would be less than the weight of a single bacterium. And yet, in the vacuum of space where there is no friction, no air resistance, no force to counteract this tiny, persistent push, a solar sail accelerates continuously. Slowly at first, almost imperceptibly. But day by day, week by week, the velocity builds. The smaller and lighter the spacecraft, the greater the acceleration per unit of force. The larger the sail, the more photons it catches. The combination of minimal mass and maximal area, pursued to its logical engineering extreme, begins to produce numbers that challenge the assumptions we have been building. Japan's Ikaros spacecraft interplanetary kite craft, accelerated by radiation of the sun, launched in May of 2010 as a secondary payload alongside the Akatsuki Venus mission, demonstrated for the first time that solar sailing actually works in deep space. Not in theory, not in a vacuum chamber on Earth. In actual interplanetary space in the real solar environment with real photon pressure against a real sail. Ikaros deployed a 14-meter diagonal polyimide membrane, 7.5 microns, thick, thinner than a single human hair, from a spinning spacecraft bus. The deployment worked, the sail unfurled. Instruments aboard measured the subtle acceleration. Over the following months, Ikaros used solar pressure alone to alter its trajectory, spiraling gently toward Venus, while its engineers on Earth watched the velocity data confirm what the theory had long predicted. It was a small victory in the grand scheme of what interstellar travel requires. Ikaros moved at velocities measured in kilometers per second, not tens of thousands. Its journey to Venus, while historic, was measured in millions of kilometers, not trillions, but it proved with the only currency that ultimately matters in engineering empirical data that the concept is real. The question became, how far can it scale? The limitation of solar sailing for interstellar purposes is the same as the limitation of everything that depends on the sun. The sun's radiation follows an inverse square law. Double your distance from the sun and the light pressure on your sail drops to 1/4 of what it was. By the time a solar sail spacecraft reaches the orbit of Jupiter, it is receiving less than 4% of the radiation it would experience near Earth. Beyond the heliosphere, the sun's light is a whisper indistinguishable from background starlight. All the useful acceleration happens close to the sun, in the fierce inner solar system where radiation remains intense. This means that to maximize final velocity, a solar sail must swing through perihelion, the closest point of its solar approach, as deep into the sun's gravity well as the sail material can physically survive. Temperatures at these distances approach and exceed 2000 degrees Celsius. The sail must not melt, tear buckle, or lose its reflectivity in this inferno. The spacecraft bus behind the sail must withstand the thermal environment without its electronics being cooked. Even under the most optimistic assumptions, perfect materials, perfect trajectory, sail, surviving perihelion at the minimum safe distance, solar sailing alone might achieve final velocities of a few hundred kilometers per second. Fast by human standards, but still requiring thousands of years to cross to Proxima Centauri. Solar sailing alone is not the answer, but solar sailing contains the seed of the answer. And to find it, someone needed to ask a different question. Not how do we make the sail bigger, but what if the light source wasn't the sun? What if the light never faded with distance because it was not emanating from a sphere in all directions, but focused into a beam aimed precisely, sustained, indefinitely, tracking the receding spacecraft across the void? What if the sail were not pushed by a star, but by a laser? The physics of laser-driven sails is in principle the same as solar sailing. Photons striking a reflective surface transfer momentum, but a laser produces coherent, monochromatic light that can be focused into a narrow beam, maintaining intensity across distances that would reduce sunlight to irrelevance. A sufficiently powerful laser array, properly engineered and aimed with extraordinary precision, could accelerate a lightweight spacecraft to velocities completely beyond the reach of any propulsion system that relies on carrying fuel. The calculations, when performed with realistic assumptions, produce a number that changes the entire conversation: 20% of the speed of light. At 20% of light speed, 60,000 kilometers per second, a spacecraft would reach Proxima Centauri in approximately 21 years. 21 years. Not 73,000, not 17,000, not 1,200. 21. A span of time within a human career. A mission that scientists who design it might live to see completed. A journey that, while still extraordinary in its demands, falls within the domain of things a civilization might actually attempt, plan, fund, and execute within a single generation. This is the number that Breakthrough Starshot announced in April of 2016 by investor Yuri Milner and physicist Stephen Hawking built its entire architecture around. And it is the number that finally, for the first time in the history of interstellar propulsion thinking, feels like a crack in the wall. But feeling like a crack and being a crack are different things. And the challenges standing between a laser sail concept and a functional interstellar probe are formidable enough to occupy the next stage of our journey entirely. For now, hold the number 21 years. For the first time in this exploration of the impossible, something almost begins to feel possible. Almost. Before the laser sail, before the gram-scale spacecraft, before any of the elegant, miniaturized thinking that defines the modern conversation about interstellar propulsion, there was a different dream. Older, louder, and in many ways, more audacious than anything that came after it. A dream that did not try to sidestep the energy problem through cleverness or efficiency. A dream that looked directly at the scale of energy required to cross interstellar distances and said, then we will use the most energetic thing we have ever built. We will ride the bomb. Project Orion was born in the late 1950s at the Los Alamos National Laboratory in the same buildings, and among some of the same minds that had designed the nuclear weapons used to end the Second World War. The basic concept was proposed by Stanislaw Ulam, one of the mathematicians central to the Manhattan Project, and developed in serious engineering detail by a team that included Freeman Dyson, one of the most brilliant theoretical physicists of the 20th century, and Ted Taylor, widely regarded as the most gifted nuclear weapons designer America ever produced. The concept was this: a spacecraft massive and robust would carry thousands of small nuclear devices in its payload bay. At regular intervals, these devices would be ejected behind the craft and detonated at a carefully calculated distance. The expanding sphere of superheated plasma stops not steel pusher plate, stop absorbers. Stop absorbers would convert the violent, repetitive hammer blows of successive nuclear detonations into smooth, continuous forward acceleration. The engineering studies produced designs of extraordinary ambition. The largest Orion concept envisioned a spacecraft 400 meters across, larger than the Empire State Building, laid on its side with a pusher plate 100 meters in diameter. It would carry approximately 300,000 nuclear devices. It would weigh on the order of 8 million metric tons at launch, and it would work. This is the part that must be emphasized because Orion is sometimes dismissed as the fever dream of Cold War excess. It was not. Freeman Dyson, who spent 2 years working on the project full-time and remained one of its most eloquent advocates for the rest of his long life, was emphatic on this point. The physics was sound. The engineering was solvable. Scaled tests using conventional chemical explosives demonstrated that the pusher plate concept functioned as predicted, that you could repeatedly detonate explosives behind a plate and produce smooth, controlled acceleration without destroying the vehicle. Dyson calculated that a nuclear pulse spacecraft using fission devices could reach velocities of approximately 1.3% of light speed. With fusion devices, hydrogen bombs rather than atomic bombs, the performance improved dramatically. Theoretical estimates placed fusion pulse Orion vehicles at velocities between 3 and 10% of light speed, depending on design specifics and mission architecture. At 3% of light speed, a spacecraft would reach Proxima Centauri in approximately 140 years. 140 years, still longer than a human lifetime, still requiring either multi-generational crews or some form of suspended animation or a crew of robotic systems. But 140 years is not geological time. It is not 17,000 years. It is not 73,000. It is a span of time that human institutions, universities, governments, scientific organizations have successfully maintained continuity across before. The Catholic Church has been operating continuously for 2,000 years. The United States has maintained constitutional governance for nearly 250. Oxford University has been teaching students for 9 centuries. 140 years is imaginable, not easy, not simple, but imaginable. Dyson himself believed that Orion represented humanity's genuine path to the stars. Not a way station on the road to something better, but the actual mechanism by which our species would first leave the solar system. He spoke about it with a clarity and conviction that carried weight precisely because Dyson was not a romantic. He was a physicist. He dealt in calculations, and then the Partial Nuclear Test Ban Treaty of 1963 ended the project. The treaty signed by the United States, the Soviet Union, and the United Kingdom prohibited nuclear weapons tests in the atmosphere, in space, and underwater. Whatever its merits as an arms control measure, and they were real, the treaty made Project Orion illegal. You cannot propel a spacecraft with nuclear detonations in space if nuclear detonations in space are prohibited by international law. The project was cancelled. The hardware was scrapped. Dyson, who had given 2 years of his life to the work, spent decades afterward writing with barely concealed grief about what had been abandoned. The universe does not care about treaties. The distances remain what they are. The energy requirements remain what they are. And the human beings who might one day attempt to cross those distances will eventually be forced to confront the same arithmetic that Orion's designers confronted in the 1950s. Whether they arrive at the same solution or a different one remains to be seen, but the lesson of Orion is permanent. The energy available from nuclear reactions is sufficient in principle to propel a vehicle across interstellar distances within timescales approaching human comprehension. The obstacle is not physics. The obstacle is politics, and politics, unlike physics, can change. A decade after Orion's cancellation, a variation on the nuclear pulse concept emerged from a different direction. In the 1990s, a physicist named John Dale Solomon at Los Alamos, the same laboratory where Orion had been born, developed what he called the Medusa concept, and it addressed one of Orion's fundamental engineering problems with a solution of considerable elegance. Orion's pusher plate had to be massive. It was positioned directly behind the spacecraft, absorbing the full violence of sequential nuclear detonations. Every explosion hammered it. Every gram of steel in that plate was dead weight, contributing nothing to the mission except structural survival. The plate had to be thick enough to withstand thousands of nuclear blasts without failing, and this requirement drove the total spacecraft mass to figures that strained even the prodigious energy output of nuclear weapons. Solomon's insight was to invert the geometry entirely. In the Medusa design, the spacecraft does not push from behind, it is pulled from in front. An enormous lightweight canopy resembling a parachute or spinnaker more than a metal plate is deployed ahead of the spacecraft on long tethers. Nuclear devices are detonated between the canopy and the spacecraft. The expanding plasma from each explosion pushes against the canopy's inner surface. The tethers, acting as shock absorbers, transfer this force to the spacecraft as smooth forward acceleration. The critical difference is in the word lightweight. Because the canopy does not absorb direct impact from the explosion, it catches the expanding plasma from a distance, the way a parachute catches air. It can be made from thin, relatively delicate material. It does not need to be a thick steel plate. It can be a large gossamer structure that mass is a fraction of what Orion's pusher plate required. And because mass is everything in rocket science, this reduction cascades through the entire mission architecture, improving performance substantially. Solomon's calculations suggested that Medusa could outperform conventional Orion designs by a factor of several times, potentially achieving velocities approaching 5% of light speed with fusion devices. At that speed, the journey to Proxima Centauri would require roughly 84 years, within a single very long human lifetime, within a mission timeline that a person could in principle devote their entire career to and still live to receive data from. The concept never progressed beyond theoretical studies for reasons that echo Orion's fate. the political barriers to launching nuclear devices into space remain. The engineering of a gossamer canopy surviving repeated nuclear plasma impacts raises materials questions that have not been experimentally tested. The social acceptability of a spacecraft that detonates thousands of nuclear weapons as it departs the solar system is at minimum complicated. But Medusa taught something important. The lesson was not merely that nuclear pulse propulsion could be improved. The lesson was that the geometry of force application matters enormously, that the shape of the problem, where the energy source is, where the receiving surface is, how force is transferred from one to the other, is as important as the magnitude of the energy itself. And this lesson, absorbed and transformed, leads directly to the concept that finally made interstellar travel feel like something more than mythology. If you can pull a spacecraft from in front, rather than push it from behind, what is the largest possible distance between the energy source and the receiving surface? What if the energy source stayed home? The idea of using laser light to propel spacecraft was first proposed seriously by physicist Robert Forward in 1962, only a year after the first working laser was demonstrated in a laboratory. Forward was a remarkable figure, a physicist at Hughes Research Laboratories with a professional obligation to practical engineering and a personal inclination toward ideas that existed at the extreme outer boundary of what physics permitted. He thought in decades and centuries rather than budget cycles. He wrote technical papers about interstellar travel the way other physicists wrote papers about particle accelerators, with the assumption that the question deserved serious mathematical treatment regardless of near-term feasibility. Forward's insight was this: a laser produces coherent light that diverges far less than sunlight as it travels. A sufficiently large laser aperture could maintain a usable beam intensity across distances measured not in millions of kilometers, but in light years. If you built such a laser, enormous, yes, but not physically impossible, and aimed it at a lightweight reflective sail attached to a small spacecraft, you could accelerate that spacecraft to velocities determined not by how much fuel it could carry, but by how much power you were willing to generate and beam across space. The sail experiences force as long as the beam hits it. The beam can follow the spacecraft across the solar system, across the inner region of interstellar space, for as long as tracking precision allows, and the laser continues to operate. Every moment the beam is on and hitting the sail, the spacecraft accelerates. There is no propellant to exhaust. There is no fuel to run out. There is only the continuing transfer of photon momentum from laser to sail to spacecraft velocity. Forward calculated that with a laser array of sufficient power and a sail of sufficient area and minimal mass, a spacecraft could be accelerated to a significant fraction of light speed. The numbers he published were, by the standards of 1962, almost science-fictional in their ambition. He proposed laser arrays radiating power in the gigawatt to petawatt range, sails kilometers across, spacecraft accelerating at fractions of Earth's gravity for months. The physics was correct. It remains correct today. No subsequent analysis has found an error in Forward's fundamental reasoning. What seemed like speculation in 1962 is still more than 6 decades later among the most physically credible paths to interstellar velocities that has ever been proposed. The obstacles are not in the equations, they are in the engineering. To accelerate a spacecraft to 20% of light speed using laser propulsion requires energy delivery on a scale that dwarfs any single human project in history. The calculations depend heavily on spacecraft mass. This is why mass becomes absolutely central to everything that follows. But even for a spacecraft weighing a single gram, the kinetic energy at 20% light speed is approximately 300 megajoules, roughly equivalent to the explosive yield of 70 kilograms of TNT delivered through a laser beam in a matter of minutes. For a spacecraft weighing not 1 gram but 1 kilogram, a more conventionally conceivable size, the energy requirement scales by a factor of 1,000. And the laser array must deliver all of this energy precisely continuously to a sail that is receding at accelerating velocity across distances, growing from kilometers to millions of kilometers to billions of kilometers, maintaining beam focus against the fundamental diffractive spreading that affects all electromagnetic radiation. Beam divergence is the central optical challenge. No matter how precisely a laser is focused, the beam spreads as it travels. This is not an engineering imperfection that can be eliminated with better optics. It is a consequence of wave physics described by the same mathematics that governs all electromagnetic phenomena. The rate of spreading depends on the laser's wavelength and the diameter of the aperture through which it is emitted. Shorter wavelengths spread less. Larger apertures spread less. To maintain a usable beam intensity across the distances required for sustained acceleration, not just within Earth orbit, but across tens of millions and eventually hundreds of millions of kilometers, the laser aperture must be enormous. Studies associated with breakthrough starshot suggest aperture diameters of kilometers, potentially tens of kilometers, for the most ambitious mission architectures. These are structures larger than any humans have ever built in space, larger than any currently planned space construction, not physically impossible but requiring industrial capabilities in orbit or on the lunar surface that lie decades beyond our current reach. The power generation requirements are similarly staggering. Gigawatts of laser power, the output of multiple large nuclear power plants concentrated phase-coherent, precisely aimed and sustained for the duration of the acceleration phase. The waste heat alone from operating such a system requires radiator arrays spanning square kilometers. The infrastructure supporting the lasers must be built, maintained, and operated continuously across the months or years of a mission's acceleration phase. And all of this infrastructure stays home. It never moves. It points at a sail that is shrinking into the distance, tracking it with angular precision that must be maintained to within fractions of an arcsecond across distances of millions of kilometers. The engineering is not impossible. The physics permits it, but the gap between what the physics permits and what human civilization currently possesses is a gap measured not in decades, but in generations of sustained, focused, adequately funded development. This is the landscape into which Breakthrough Starshot arrived in April of 2016. The announcement came at One World Observatory in New York City. Yuri Milner, the Russian-born technology investor, who had already funded significant scientific initiatives through his Breakthrough Prize and Breakthrough Listen programs, stood alongside Stephen Hawking, one of the most recognizable scientific figures on Earth, and described a project that would attempt to do what every propulsion concept in this history had so far failed to accomplish: reach another star within a human lifetime. The project allocated $100 million for initial research and development. It assembled an advisory committee that included some of the most respected physicists, aerospace engineers, and planetary scientists in the world. Pete Worden, former director of NASA's Ames Research Center, agreed to serve as executive director. Avi Loeb of Harvard's astronomy department joined as chair of the advisory board. This was not a group of enthusiasts gathering at a science fiction convention. This was serious institutional commitment from people with serious reputations, backed by serious money, pursuing a specific engineering target with specific timelines and specific technical milestones. The Starshot architecture emerged from a constraint-driven optimization process. The question was not, how do we build the best interstellar spacecraft? The question was, given what we know about laser propulsion physics, what spacecraft design minimizes the laser array size and power requirements while still achieving the target velocity and delivering useful science? The answer was miniaturization taken to its logical extreme. Make the spacecraft as small as physically possible. Kinetic energy scales linearly with mass. A spacecraft 100 times lighter requires 100 times less energy to accelerate to the same velocity. A spacecraft 1,000 times lighter requires 1,000 times less energy. If the spacecraft can be reduced not to kilograms or even grams, but to fractions of a gram, the mass of a small insect, the mass of a few sequins, then the laser array requirements, while still formidable, begin to approach the realm of what might actually be built within a century of development. The Starshot team proposed spacecraft they called Starchips. Each Starchip would be fabricated on a single silicon wafer, approximately 4 centimeters square, integrating on a single chip the cameras, spectrometers, attitude sensors, communication systems, and computer processing needed for an interstellar flyby mission. Mass somewhere between 1/10 and 1 gram depending on the final design. The sail attached to each star chip would be a reflective membrane a few meters across, perhaps 2 to 4 meters in diameter, made from materials engineered to reflect the laser's specific wavelength with maximum efficiency, while massing only a fraction of a gram per square meter. Total system mass, star chip plus sail, would be measured in grams. At these masses, the laser array requirements, while still requiring gigawatts of power and apertures measured in kilometers, become at least theoretically achievable within a multi-decade development program. The Starshot team estimated that with sustained investment and progress across multiple fronts — materials science, photonics, microfabrication, phased array, laser technology — a functional system might be launchable within 20 to 30 years of the program's announcement. That places first launches somewhere between 2036 and 2046. After launch, the laser array would fire for approximately 10 minutes. In those 10 minutes, each star chip and its sail would accelerate from essentially 0 to 20% of light speed. The acceleration, required roughly 10,000 times the force of Earth's gravity, would be lethal to any biological organism and damaging to many conventional electronic systems. But a properly designed silicon chip with no moving parts, no fragile biological tissue, no delicate chemical systems might survive. After 10 minutes, the laser shuts off. The star chip coasts. For 20 years it travels through interstellar space at 60,000 kilometers per second, decelerating from nothing. There is no braking system, no fuel for orbital insertion, no mechanism for slowing down. The mission is a flyby. The star chip passes through the Proxima Centauri system at full velocity, spending perhaps a day in the vicinity of the star, perhaps hours near Proxima b, if trajectory calculations bring it close enough, taking images measuring magnetic fields, analyzing whatever atmospheric signals it can detect, and then continuing outward into the deeper void beyond. In those few hours it must gather everything it will ever know about Proxima b, and then it must send that data home, across 4.2 light-years of space, using a transmitter that masses less than the paper this script is written on, powered by a system drawing milliwatts of electricity. The data transmission problem is in some ways the most quietly daunting challenge in the entire Starshot architecture. The signal from a star chip at Proxima Centauri, transmitted by the world's smallest antenna across 40 trillion kilometers, would arrive at Earth with a power measured in the neighborhood of 10 to the power of -30 watts. This is not merely weak. This is a signal that requires Earth-based receiving dishes of significant size arrays of large telescopes coordinated across baselines of kilometers, combined with signal processing algorithms, extracting coherent data from noise flaws that would otherwise completely bury the transmission. The data rate under optimistic assumptions would be measured in bits per second. A single low-resolution image might require hours to transmit. A high-resolution image of Proxima b's surface, if the flyby trajectory brings the star chip close enough to image it, might take days. Every bit of data must be prioritized before the mission launches. The onboard algorithms pre-programmed to decide autonomously what to observe and what to transmit, because there will be no opportunity to send updated instructions and receive a response in time to affect the flyby. The mission is, in this sense, not a conversation between Earth and spacecraft. It is a message, sent 20 years in advance, encoded in the spacecraft's programming, executed faithfully in a star system 4 light-years away, and then the reply carrying whatever Proxima b has to say, taking another 4 years to cross back. 24 years from launch to first data. A generation's worth of waiting for a few hours of observation. And yet, and this is what matters, those few hours of observation would be the first time in the history of our species that an instrument built by human hands gathered data from another star system. The first time we would know, not by inference and statistical modeling and the interpretation of stellar wobbles and transit curves, but by direct measurement, something true about the surface or atmosphere of a world orbiting another sun. The first time in 4 billion years of Earth's existence that something originating from this planet touched another star's light. That is worth 24 years of waiting. That is worth the laser array and the billion-dollar development program and the decades of engineering and the countless failures and near failures that will precede any successful launch. Not because the data will necessarily answer every question we have about Proxima b. Not because a flyby at 20% light speed with a gram-scale spacecraft carries the same scientific payload as an orbiting observatory, but because it represents the moment the barrier breaks. The first crack in the wall that has kept every star beyond our reach since the first human looked up and wondered. The first is always the hardest. The first is always the one that changes what is possible. Space in the popular imagination is empty. This is not entirely wrong. The interstellar medium, the material filling the vast gulf between stars, is by any terrestrial standard a vacuum more perfect than anything achievable in the most advanced laboratory on Earth. A cubic centimeter of the best vacuum humans have ever produced in controlled conditions contains approximately 100,000 molecules. A cubic centimeter of interstellar space contains on average roughly 1 atom, sometimes less. In the regions between stellar systems, you could travel for billions of kilometers without encountering a single particle of matter larger than a hydrogen nucleus. By the standards of daily life, by the standards of chemistry and engineering and every physical intuition built from a lifetime on a planet with an atmosphere, this is emptiness. So profound it barely registers as a physical environment at all. It is closer to nothing than to anything we experience as something. But a star chip traveling at 20% of the speed of light does not experience this near nothingness the way a stationary observer does. At 60,000 kilometers per second, the geometry of collision changes entirely. What matters is not how many particles occupy a cubic centimeter of space at any given moment. What matters is how many particles the spacecraft encounters per second as it sweeps through that space at relativistic velocity. At 20% of light speed, a starship crosses 1 centimeter of space in approximately 170 femtoseconds, 170 quadrillionths of a second. In one single, every atom along that 60,000 kilometer column of space, every hydrogen nucleus, every helium atom, every trace molecule of carbon monoxide or water ice or interstellar dust collides with the leading edge of the spacecraft at a relative velocity that transforms each encounter from a gentle nudge into something with genuine destructive power. The numbers, when calculated with care, are sobering. A single hydrogen atom massing approximately 1.67 times 10 to the negative 27th kilograms, striking a surface at 20% of light speed, carries kinetic energy of approximately 3 times 10 negative 12th joules, 3 picojoules. This sounds negligible. It is not. 3 picojoules deposited into a silicon chip across an impact area, measured in angstroms, the scale of atomic dimensions, creates a local energy density equivalent to a small explosion at the nanoscale. The impacting atom displaces neighboring atoms in the chip's crystalline lattice. It creates defects. It deposits charge in sensitive transistor junctions. It degrades the material it strikes in ways that accumulate with every subsequent impact. Over a journey of 4.2 light-years, a starship traveling at 20% of light speed will encounter approximately 100,000 hydrogen atoms per square centimeter of frontal area. 100,000 individual atomic impacts per square centimeter each, delivering enough energy to damage the lattice structure of the materials it strikes. For the electronics, this is radiation damage. The same phenomenon that degrades solar cells on long-duration space missions, that corrupts memory in spacecraft computers after years of cosmic ray exposure, that motivated the extensive radiation hardening programs in every serious space electronics development effort. Radiation damage in silicon creates electron-hole pairs, introduces charge-trapping states, shifts threshold voltages in transistors, and ultimately causes bit errors, logic failures, and component degradation. On a mission lasting 20 years, through the interstellar medium at relativistic velocity, the cumulative radiation dose received by a starship's electronics would be extraordinary. Engineers working on the Starshot concept have estimated that the total ionizing dose experienced by a starship over its 20-year cruise would be roughly equivalent to decades of operation in the most intense radiation belts surrounding Jupiter, an environment that kills unshielded commercial electronics in hours and requires heavy radiation hardening even for purpose-built space instruments. The chip must be designed from the outset to tolerate this dose without accumulating enough errors to compromise its mission-critical functions. This is solvable in principle. Radiation-hardened electronics exist and are routinely used in military and space applications, but it requires design choices that add complexity and potentially mass to an architecture where every milligram matters. The dust is worse. Interstellar dust grains, particles of silicate, carbon, iron, and ice ranging in size from nanometers to micrometers, are sparsely distributed through the interstellar medium. Their average density is extraordinarily low. In a typical region of the galactic disk, there is approximately 1 dust grain per trillion cubic meters. This sounds and is genuinely rare. If you were floating in interstellar space and tried to find the nearest dust grain with the naked eye, you would wait a very long time. But a starship sweeping through this sparse field at 60,000 kilometers per second accumulates encounters at a rate determined by its cross-sectional area and the column density of material along its path. Over 4.2 light-years, a sail several meters in diameter sweeps through a cylinder of space containing, by best current estimates, thousands to tens of thousands of individual dust grains of various sizes. Most of these grains are nanometer scale, smaller than the wavelength of visible light, essentially individual large molecules rather than macroscopic objects. A nanometer scale grain striking a surface at 20% of light speed carries kinetic energy roughly equivalent to that of a rifle bullet striking a target, per grain, per impact, not in total, per individual grain. A grain of interstellar dust, 1/10,000th of a millimeter across, colliding with a starship's sail at 60,000 kilometers per second, releases energy equivalent to a small caliber bullet impact into a surface area measured in nanometers. The result is not a dent, it is a local plasma explosion. The grain and a small volume of sail material are instantly vaporized, creating a brief flash of superheated plasma and leaving behind a crater orders of magnitude larger than the impacting grain. Across thousands of such impacts distributed over the sail's several-meter surface, the cumulative damage is significant. Each impact punches a hole. Each hole reduces the sail's effective reflective area, diminishing the laser's ability to push the spacecraft. Structural integrity may be compromised if the distribution of impacts is unlucky enough to cluster along stress lines. The gossamer membrane, engineered to be as thin as possible to minimize mass, has limited tolerance for such damage. And this is for dust grains measured in nanometers. Occasionally, a grain measured in micrometers, still invisible to the naked eye, still a speck that would be lost on the surface of a human hair, will be encountered. A micrometer-scale grain at 20% of light speed carries kinetic energy comparable to an artillery shell. The impact would be catastrophic for any component it struck directly. This is where the breakthrough starshot strategy of numbers reveals its true logic. If you are sending a single spacecraft, these impact probabilities are mission-threatening. The probability that a single starship survives the full 4.2 light-year journey through the interstellar medium without suffering a catastrophic impact cannot be calculated with certainty given remaining uncertainties in interstellar dust distribution. Conservative estimates place the single spacecraft survival probability somewhere between 10 and 50%, depending on assumptions about dust density along the specific trajectory and the robustness of the sail material. A 50% survival probability is not acceptable for a mission that represents humanity's first interstellar probe, costing billions of dollars, requiring decades of development, carrying the hopes of a generation of scientists. You do not launch one and hope. But what if you launch 1,000? At a 50% individual survival probability, 1,000 launched starships would deliver approximately 500 functioning probes to the Proxima Centauri system. Even at a 10% survival rate, representing a far more hostile interstellar environment than current models suggest, 1,000 launches would yield 100 survivors. 100 independent spacecraft arriving at Proxima b from slightly different trajectories, imaging it from slightly different angles, measuring its magnetic field and particle environment with redundant instruments transmitting their data independently through separate communication channels. The redundancy is not merely insurance against individual failures, it is science. Multiple flyby trajectories sample different regions of the Proxima Centauri system. Multiple independent measurements of the same phenomenon reduce statistical uncertainty. Multiple independent transmissions of the same data increase the probability that the information arrives at Earth intact, even if some individual transmission channels are corrupted by interstellar plasma or equipment degradation. The strategy transforms the interstellar medium from an adversary into a manageable statistical problem. You do not need to build a spacecraft robust enough to guarantee survival. You need to build spacecraft cheap enough and mass-producible enough that you can send enough of them to guarantee mission success regardless of individual losses. This insight, survival through numbers rather than survival through robustness, is borrowed consciously or not from principles that nature discovered billions of years before humans began thinking about space travel. A salmon does not survive to reproduce by being individually indestructible. It survives because thousands of its siblings make the same journey, and the small fraction that avoid every predator and obstacle is sufficient to sustain the population. A dandelion does not guarantee the survival of any single seed. It releases thousands into the wind and trusts the mathematics of probability. Starshot proposes to explore the stars the way evolution has always solved difficult problems, not by building one perfect solution but by generating enough attempts that the failures become irrelevant. The manufacturing implications of this strategy are profound. Traditional spacecraft are hand-built artifacts. Each one is unique. Each one is tested individually. Each subsystem undergoes qualification campaigns lasting months or years. The James Webb Space Telescope cost approximately $10 billion and required more than 20 years from initial concept to operational deployment. It is arguably the most precisely engineered object humanity has ever placed in space. You cannot build 1,000 James Webb telescopes to send to Proxima Centauri, but you can build 1,000 starships. Because starships are not hand-built artifacts, they are semiconductor devices fabricated using the same photolithographic processes that manufacture the processor in your telephone. A single silicon wafer, 30 centimeters in diameter, can yield hundreds of individual chips in a single production run. The incremental cost per chip once the fabrication process has been developed and the tooling amortized approaches tens or hundreds of dollars rather than billions. Mass production compresses per unit costs through the same economics that reduced the price of transistors from dollars each in the 1950s to effectively zero today. The sales present a different but not incomparable challenge. Large area thin film deposition, the same basic technology used to manufacture solar cells, flexible electronics, and certain types of optical coatings, could in principle produce square meter scale reflective membranes, costs far below traditional spacecraft components. The membranes would be manufactured in batches folded for compact stowage in a deployment container and attached to starships before launch. The entire assembly chip plus sale might cost thousands of dollars in mature production, not millions. This economic architecture changes the character of interstellar exploration entirely. Instead of a single national prestige mission representing the accumulated ambition of a civilization launching once with the full weight of expectation on its shoulders, the Starshot model imagines a continuous iterative program. Early generations of starships launched with technology available in the next decade might fail at high rates, but each generation of failures teaches something. Dust impact data, radiation tolerance data, sail deployment data, laser tracking data. Each failed mission returns information that improves the next generation's design. By the time a generation of starships is reliable enough to complete the full interstellar journey, the architecture will have been refined through hundreds of iterative experiments, most of them failures, all of them educational. But surviving the journey is only part of the problem. At the end of 20 years of travel, as the Starship approaches the Proxima Centauri system at 60,000 kilometers per second, it faces a challenge that no amount of manufacturing, elegance, or statistical strategy can address through numbers alone. It must look, and then it must tell us what it sees. The imaging challenge is deceptively severe. At 20% of light speed, the starship traverses the distance from Proxima Centauri itself to Proxima B's orbital radius, roughly 7.5 million kilometers in approximately 2 minutes. The window during which the planet is close enough to image at useful resolution moving across the chip's field of view at enormous angular velocity lasts somewhere between seconds and minutes depending on flyby geometry. In this window, the onboard camera, a device smaller than the camera in a smartphone, drawing milliwatts of power, operating at a temperature that varies with the stellar environment from near absolute zero in deep space to potentially hundreds of degrees as the spacecraft passes through the inner system, must capture images at a resolution sufficient to answer the questions the mission was designed to ask. Does the planet have an atmosphere? Are there clouds? Is there liquid on the surface? Are there patterns of reflectance that might suggest geological, or in the most extraordinary scenario, biological processes? The pixel resolution achievable by a centimeter-scale optical system at a flyby distance depends on the optic's aperture and the distance at closest approach. Engineering teams have proposed trajectories that bring starships within tens of thousands of kilometers of Proxima b, close enough with a carefully designed optical system to achieve resolutions of tens of kilometers per pixel. This would be sufficient to detect the presence or absence of an atmosphere through limb-scattering observations, to identify broad-scale surface geology, to measure the planet's albedo in multiple wavelength bands. It would not be sufficient to detect cities if cities existed. It would not resolve individual geographical features with the clarity of a satellite image. But it would be sufficient to answer definitively whether this world has air, whether it has ice, whether it has liquid water in some form, whether its surface bears any spectroscopic signature suggesting chemical processes of interest to the question of life. These would be the most important observations in the history of science. And then they must be transmitted home. The communication system of a starship represents the most constrained element of the entire architecture. The transmitter must be integrated on the chip or the sail structure, massing fractions of a gram, drawing power from tiny photovoltaic cells, receiving the light of a red dwarf star that is intrinsically dimmer than our own sun. The signal must travel 4.2 light-years, 40 trillion kilometers, before arriving at Earth. By the time it arrives, the signal will have spread across an area of space vastly larger than the Earth itself. The fraction of the transmitted energy that intersects our planet's surface is infinitesimal. Detecting it requires the largest radio telescope arrays on Earth, pointed continuously at Proxima Centauri, running signal processing algorithms at the boundary of what is computationally feasible. The data rate under the most optimistic assumptions about transmitter efficiency and receiver sensitivity would be measured in single digits of bits per second. Perhaps a few hundred bits per second with the most advanced phased array optical communication systems currently being studied. A high-resolution image of Proxima b, 1 megabyte of compressed image data, would require approximately 22 hours to transmit at 100 bits per second. To receive it at Earth, after the 4-year light travel delay, mission controllers would spend nearly a day watching individual bits arrive, assembling them into the first true portrait of another world. That image would be worth every year of development, every dollar of investment, every engineering failure and redesign and delayed launch that preceded it, because for the first time it would not be a point of light. It would not be a statistical inference from a stellar wobble or a transit curve. It would be a world, seen, real, known. A photograph of the answer to a question humanity has been asking since the first night, that the first conscious mind looked up at the stars and wondered whether anything looked back. The interstellar medium, then, is not merely the empty space a spacecraft must cross. It is an active environment, hostile, probabilistic, filled with particles moving at relative velocities that transform the mundane into the lethal. The strategy for crossing it successfully is not to build a single indestructible machine. It is to build thousands of fragile ones and send them all trusting the mathematics of probability to deliver enough survivors. This is not defeat, it is wisdom. The universe does not bend its rules for anyone. It does not reduce the density of interstellar dust because a spacecraft is important. It does not slow the cosmic rays because a chip contains irreplaceable electronics. It does not narrow the 4-light-year gulf because humans are impatient. What the universe does permit, what the physics has always permitted waiting for the engineering to catch up, is cleverness. The clever application of existing principles to produce outcomes that seem from a distance miraculous. The same photon momentum that Kepler noticed pushing comet tails harnessed and focused and scaled to accelerate a gram of silicon and metal to 60,000 kilometers per second. The same semiconductor fabrication that miniaturized the mainframe computer into a device you carry in your pocket applied to the problem of interstellar spacecraft mass. The same statistical logic that drives every successful biological strategy on Earth applied to the challenge of surviving a 20-year journey through a hostile void. The stars have not moved, but humanity is slowly becoming clever enough to begin reaching for them. At the end of 20 years of travel through the interstellar dark, if everything has gone as planned, if the sail deployed cleanly, and the laser tracked true, and the dust was merciful, and the electronics survived the accumulated radiation of 2 decades in the void between stars, a starship will begin to detect something it has never encountered before. Light, not the faint background glow of the cosmic microwave radiation that has accompanied it throughout the journey. Not the distant pinprick of our own sun shrinking behind it year by year until it became indistinguishable from the surrounding stars. Something brighter, something growing. A source of reddish light strengthening over weeks and months as the spacecraft closes the final distance to its destination at 60,000 kilometers per second, Proxima Centauri. From Earth, Proxima Centauri is invisible to the naked eye. It shines at magnitude 11.1, roughly 100 times too faint to see without a telescope, even on the darkest night in the most remote location on Earth with the most sensitive human eyes. It is a red dwarf, the most common type of star in the Milky Way galaxy, and in many ways the most alien type of star to our solar system conditioned imagination. Proxima Centauri masses approximately 1/8 of the Sun's mass. Its diameter is roughly 1/7 of the Sun's diameter. If you placed it where our Sun sits, it would appear in Earth's sky as a dim orange-red disk, roughly 7 times smaller than what we are accustomed to. It radiates energy at approximately 1/6 of 1% of the Sun's luminosity, so dim that a world must orbit within 7.5 million kilometers to receive the stellar energy Earth receives at 150 million kilometers from our own more generous star. This dimness is not a deficiency. It is a different kind of existence. Red dwarfs are the most numerous stars in the galaxy, comprising roughly 70 to 75% of all stellar objects in the Milky Way. There are approximately 70 billion red dwarfs in our galaxy alone. If planets like Proxima b are common around them, and the statistics from the Kepler mission and subsequent surveys suggest they may be, then the number of potentially habitable worlds in our galaxy is not millions, it is tens of billions. Understanding what happens to a planet orbiting a red dwarf is therefore not a narrow question about one specific world. It is one of the most consequential questions in planetary science. The answer shapes our understanding of life's cosmic prevalence or rarity in ways that no other single observation could match. And Proxima b, orbiting the nearest red dwarf, is where that answer must begin. The first thing to understand about Proxima b is that it almost certainly does not rotate the way Earth rotates. Earth completes one full rotation approximately every 24 hours. This rotation, combined with the axial tilt that gives us seasons, creates the familiar rhythm of day and night, of summer and winter, that has governed the evolution of nearly every organism on our planet. The daily cycle of light and darkness shapes biology at every scale, from the molecular clockwork of circadian rhythms in individual cells to the broad behavioral patterns of entire ecosystems. Proxima b, orbiting at 7.5 million kilometers from its star, almost certainly does not share this rhythm. At such close orbital distances, the gravitational gradient across the planet's diameter, the difference in gravitational pull between the side facing the star and the side facing away, is enormous. This differential force, called tidal force, acts to break the planet's rotation over geological time, gradually slowing it until rotation rate matches orbital period. The planet then spins exactly once per orbit, always presenting the same hemisphere to its star. We call this tidal locking. The moon is tidally locked to Earth, which is why we always see the same face of the moon regardless of where it sits in the sky. Proxima b, at its close orbital distance around a gravitationally assertive star, has had approximately 4.8 billion years to reach this synchronized state. The timescale for tidal locking at such orbital distances is estimated at tens to hundreds of millions of years. Proxima b has been in its current configuration for perhaps 10 times longer than tidal locking requires. The planet almost certainly has a permanent day side and a permanent night side, separated by a terminator line that never moves. Consider what this means. On the day side, Proxima Centauri hangs in the sky without moving, not rising, not setting, not tracing an arc from dawn to dusk, simply present, always in the same position. The ground beneath it receives continuous stellar radiation 24 hours of every day for billions of years. Whatever processes govern heat evaporation, chemistry, and weather on that hemisphere operate under conditions of permanent, unrelenting illumination. The temperatures on the day side depend critically on one factor we cannot currently measure with certainty: whether Proxima b possesses an atmosphere. With no atmosphere, the day side bakes. Rocks absorb radiation and re-emit it as infrared heat, but with nothing to distribute that heat laterally. Temperatures at the substellar point, the spot on the surface directly beneath the star, could reach several hundred degrees Celsius. The night side, receiving no stellar radiation and having no atmospheric blanket to retain what little heat might diffuse from the day side, cools to temperatures approaching absolute zero. The planet becomes a world of absolute extremes, frozen on one side and scorched on the other, with nothing in between except the narrow terminator, where the star perpetually hovers at the horizon. With a thick atmosphere, everything changes. Atmospheric circulation carries heat from the day side toward the night side, moderating temperatures across the entire planet. Models of tidally locked worlds with Earth-like atmospheres suggest that heat transport could prevent both the day side from boiling and the night side from freezing entirely. The terminator region, where the star sits perpetually on the horizon, where perpetual twilight reigns, might maintain temperatures compatible with liquid water. Some models produce temperate conditions across broad regions of the day side if the atmosphere is thick enough and the circulation efficient enough. The difference between these scenarios, no atmosphere, and a thick one, represents the difference between a sterile, radiation-blasted rock and a potentially habitable world. And at 4.2 light-years of distance, with current observational technology, we cannot definitively determine which describes Proxima b. This is precisely what a Starship flyby could begin to resolve. The atmospheric question is complicated further by the nature of Proxima Centauri itself. Red dwarfs are temperamental stars. Our own Sun, a relatively calm G-type star, produces solar flares, sudden releases of magnetic energy that briefly increase its brightness and shower the inner solar system with high-energy particles. The most powerful solar flares in recorded history, like the Carrington event of 1859, disrupted telegraph systems worldwide and produced auroras visible at tropical latitudes. For Earth, protected by its magnetic field and thick atmosphere, such events are dramatic but not existentially threatening. Proxima Centauri produces flares of comparable and sometimes greater intensity on a far more frequent schedule. Observations have recorded Proxima Centauri undergoing major flare events multiple times per day during active periods. A landmark event, observed in March of 2016, announced in the same year as Proxima b's discovery, in a coincidence that struck many astronomers as cosmically ironic, produced a flash of ultraviolet radiation roughly 10 times more intense than the most powerful flare our Sun has ever produced, measured in terms of the fraction of the star's normal output. For a planet orbiting at 7.5 million kilometers, 1/20th the distance that Earth orbits the Sun, such a flare delivers a pulse of ultraviolet radiation and high-energy X-rays roughly 2,000 times more intense than the most powerful solar flare event Earth has experienced in recorded history. 2,000 times. The atmospheric implications are severe. Ultraviolet radiation and X-rays at these intensities drive photochemical reactions in the upper atmosphere that dissociate molecules, breaking them apart into their constituent atoms. Some of these atoms, particularly hydrogen, move fast enough after dissociation to escape the planet's gravity entirely. Over billions of years of such bombardment, an atmosphere can be eroded from above, not by the solar wind stripping gas away, but by the star's radiation energizing it enough to escape. Early in Proxima Centauri's history, when it was younger and more active even than it is today, this erosion would have been more intense. Red dwarfs pass through a prolonged pre-main sequence phase lasting hundreds of millions of years, during which they are far more luminous and far more flare-active than they become in maturity. Any planet forming in the habitable zone of a red dwarf spends its most volatile, rich, atmosphere-forming epoch under bombardment from a star in its most violent state. This is the gauntlet Proxima b ran. Whether it survived with atmosphere intact depends on factors we cannot currently observe. The planet's initial volatile inventory, how much water, carbon dioxide, nitrogen, and other gases it started with, matters enormously. A planet that formed with abundant volatiles might lose substantial atmosphere, yet retain enough for habitability. One that formed volatile poor might be stripped to bare rock relatively quickly. The planet's magnetic field, if it possesses one, provides critical protection. A magnetic field deflects the charged particle component of stellar radiation, the electrons and protons that constitute the stellar wind, and the energetic particle events following major flares. These particles are among the most efficient atmospheric strippers, transferring momentum to atmospheric ions and ejecting them into space. An Earth-like magnetic field reduces this stripping dramatically. A weak or absent magnetic field leaves the atmosphere exposed. Whether Proxima b generates a magnetic field connects to questions about its interior. Earth's magnetic field arises from convection in its liquid iron-nickel outer core, a process called the geodynamo, driven partly by the planet's rotation and partly by heat flowing outward from the interior. A tidally locked planet rotates much more slowly than Earth from an inertial frame which may suppress or eliminate the rotational contribution to the geodynamo. Whether tidal heating the flexing of the planet's interior by the gravitational gradient of its close orbiting star might compensate and sustain internal convection is a subject of active theoretical debate with no consensus answer. The honest summary is this: we do not know whether Proxima b has an atmosphere. We do not know whether it has a magnetic field. We do not know whether its surface temperatures permit liquid water. We do not know whether it is a sterile rock, an ice-covered world, a planet wrapped in a thick, reducing atmosphere, or something stranger that has no analogue in our solar system. We know its mass. We know its orbital period. We know its distance from its star. Everything else is inference and model and educated speculation. This uncertainty is not a failure of science. It is an honest accounting of what 4.2 light-years of distance does to observational capability. And it is the clearest possible argument for why a flyby mission, however limited its observational window, however minimal its data rate, however constrained its instrument suite, would represent the most important planetary science observation in the history of astronomy. Let us imagine for a moment what a starship might actually see. The approach phase begins weeks before closest encounter. At 20% of light speed, the spacecraft covers 60,000 kilometers every second. But Proxima Centauri is a point source for most of the journey, brightening gradually as distance decreases. The star's reddish light fills the tiny photovoltaic cells on the sail and chip, providing the power for systems that have been dormant or operating at minimal levels for 2 decades of cruise. The onboard computer, executing pre-programmed initialization sequences developed by engineers who are now 20 years older than when they wrote the code, begins powering up instruments. Cameras perform calibration routines. Spectrometers check their wavelength references against known stellar sources. Attitude sensors orient the spacecraft using the positions of surrounding stars. At roughly 1 billion kilometers from Proxima Centauri, closer than Jupiter is to our Sun, the system begins to resolve. The star is no longer a point. the instruments can distinguish its disk from the surrounding sky. And somewhere in the data, if the trajectory has been calculated correctly and the planet's orbital phase is favorable, there will be a dim point of reflected light near the star, Proxima b. The planet reflects only a tiny fraction of its star's already dim output. Detecting it against the star's glare requires careful image processing, the same techniques used by Earth-based telescopes to image exoplanets through coronagraphic methods. The Starship's computer-running algorithms developed to handle exactly this challenge begins extracting the planet's signal from the surrounding noise. In the days before closest approach, the planet brightens as the spacecraft closes in. Its angular size, invisible at first, becomes detectable, then measurable. Then, in the final hours, before the flyby itself, resolvable into a disk with discernible features. If Proxima b has clouds, the Starship will see them. Bright regions of high reflectance that move and evolve, driven by atmospheric circulation patterns unlike anything in our solar system. Permanent dayside cloud banks built by the continuous evaporation of water on the illuminated hemisphere. Dark regions on the night side, where clouds, if they form at all, are born of entirely different dynamics. If Proxima b has no clouds, if it is a bare rock with no atmosphere, the Starship will see a different kind of surface. Ancient craters, perhaps record of the bombardment every rocky world endures in its youth. Geological features shaped by billions of years of tidal stresses, the constant flexing of the crust under the gravitational gradient of the nearby star. A surface colored by the mineralogy of whatever rocks compose it, iron oxides producing a reddish-brown landscape, silicates contributing grays and whites, perhaps carbon-rich minerals, darkening broad regions to near black. The Terminator, if the flyby geometry reveals, it tells its own story. On an airless, tidally locked world, the Terminator is geologically active. The perpetual boundary between extreme heat and extreme cold creates thermal cycling that fractures rock drives. Expansion and contraction potentially generates unusual mineral formations and surface textures found nowhere else in our solar system. On an atmosphered world, the Terminator is meteorological. It is where the permanent storm systems born of the temperature differential between day and night reach their greatest intensity. Winds from the day side and the night side collide here, producing weather phenomena of a kind we have never observed directly. The spectrometer, meanwhile, is reading the light that scatters through the planet's limb, the thin atmospheric edge visible against the darkness of space during the flyby. Every gas molecule has a characteristic absorption signature, a fingerprint in wavelength space as unique as a physical fingerprint. Oxygen absorbs at specific wavelengths, carbon dioxide at others. Water vapor, methane, nitrous oxide, ozone, each leaves its mark on the spectrum of light that passes through the atmosphere. These signatures would be readable, not with certainty, not with the statistical confidence that would satisfy a scientific journal requiring 3 sigma detections from years of repeated observation, but readable enough to indicate whether the atmosphere contains the broad categories of compounds that matter for the first question: is this world alive? Because here is what makes Proxima b different from every other exoplanet we have studied through stellar transits and radial velocity measurements and direct imaging from Earth orbit. Here, for the first time, the spectrometer is not reading starlight that has passed through the atmosphere from 90 degrees away, averaged over a hemisphere, diluted by the star's overwhelming brightness. It is reading atmosphere from kilometers away in direct transmission through the limb, with signal-to-noise ratios orders of magnitude better than any Earth-based technique can achieve at this target. If there is oxygen in that atmosphere, not a trace, but a significant fraction, the kind that can only be maintained against constant chemical consumption by a biological source that continuously regenerates it, the spectrometer will see it. If there is methane alongside oxygen, a combination thermodynamically unstable, without a continuous biological source to maintain both simultaneously, against their tendency to react with each other, the spectrometer will see it. These would be biosignatures, not proof of life, not confirmation of anything beyond the possibility space. but the first observational evidence gathered by instruments built by human hands that a world beyond our solar system might harbor biology. The closest approach lasts perhaps an hour, perhaps less depending on trajectory geometry and the minimum distance achieved. At 60,000 kilometers per second, 1 hour represents a traversal of 216 million kilometers. The planet passes through the instrument field of view, is captured in its sequence of images, has its atmospheric spectrum measured, and then recedes. The spacecraft continues outward into the space beyond Proxima Centauri, its instruments beginning to power down as it moves away from the only star in this vicinity capable of powering them. And then the signal begins, compressed, prioritized, transmitted bit by bit across 40 trillion kilometers of vacuum, traveling at the speed of light toward a blue dot that is from this vantage simply one among billions of stars. 4.2 years later, on a planet where the people who built the starship have aged another 4 years, where careers have continued and families have grown, and some of the pioneers of the project have perhaps already died, the first bits of data begin arriving at the receiving arrays. The image assembles itself pixel by pixel over hours and days, and humanity sees for the first time another world. There is a thought experiment worth sitting with for a moment before we continue. Imagine you are a scientist. You have spent the better part of your career working on the most ambitious project in the history of your species. You have contributed to the design of the laser array, or the sail material, or the star chip electronics, or the signal processing algorithms that will one day extract data from a transmission arriving from 4 light years away. You have attended the meetings and reviewed the specifications and argued over the engineering trade-offs and watched the budget negotiations and celebrated the milestones and mourned the setbacks. You are present, let us say, on the day the first starships are launched. The laser fires, the sails catch the beam, the spacecraft accelerate. In 10 minutes, they are moving at 20% of light speed already, millions of kilometers away already, beyond any possibility of recovery or modification. The mission has begun. You are, let us say, 40 years old on this day. The starships will reach Proxima Centauri in 20 years. You will be 60. The data they transmit will take 4.2 years to reach Earth. You will be 64. If the mission succeeds, if enough starships survive the journey, if the instruments function through 2 decades of interstellar radiation, if the flyby trajectory brings them close enough to Proxima b to gather meaningful observations, if the transmission systems work well enough to send the data home, you will, at 64 years old, begin receiving the first images of another world. This is the optimistic scenario. This is the scenario where everything works. And even in this best possible case, the most consequential scientific data return in human history will arrive when you are an old person 24 years removed from the moment you watch those sails catch the laser light. I thought, we are doing this. We are actually doing this. Now, consider the less optimistic scenarios. The laser array takes 30 years to build rather than 20. You are 50 when the first launches occur. You will be 74 when the first data arrives. Or 60, or 70, or you will not be alive at all. This is the temporal reality of interstellar exploration, not as an abstract philosophical observation about the scale of the cosmos, but as a practical constraint that shapes every aspect of how such a mission must be conceived, funded, organized, and sustained. The people who do the hardest work, who solve the most difficult engineering problems, who make the key breakthroughs, who carry the project through its darkest periods of budget shortfalls and technical failures, and institutional skepticism, many of them will not live to see the result. This has always been true of the grandest human endeavors. The architects of the great medieval cathedrals knew they would not see the spires completed. The engineers who designed the transcontinental railroad understood they were building infrastructure for a future they would not inhabit. The scientists who laid the theoretical foundations for quantum mechanics in the 1920s could not have fully imagined the world their work would create by the end of the century. But interstellar exploration takes this multi-generational character and makes it explicit, unavoidable, written directly into the physics. The light travel time cannot be negotiated. The 20-year cruise phase cannot be accelerated through institutional will or additional funding. The mission timeline is set by the speed of light. and the distance to Proxima Centauri, and neither of those quantities cares about human impatience or human mortality. This is not a problem to be solved. It is a condition to be accepted, and the acceptance of it requires a kind of thinking about time and legacy and collective purpose that our civilization is not at present particularly well practiced in. The communication delay imposes constraints that go beyond the merely inconvenient. They alter the fundamental character of what interstellar exploration can be. Every space mission humanity has conducted operates within a framework of ongoing dialogue between the spacecraft and its controllers on Earth. Even the most distant missions in our solar system, the Voyager probe's New Horizons during its Pluto flyby, the Cassini spacecraft orbiting Saturn maintained communication loops measured in hours. Voyager 1's current signal takes approximately 22 hours to reach Earth. This is slow enough to prevent joystick control, but fast enough for daily command uploads. Mission controllers can observe a developing situation, discuss it, reach a decision, and transmit new instructions with a reasonable expectation that the spacecraft will execute them before the relevant window closes. A probe at Proxima Centauri operates under entirely different conditions. A signal transmitted at the moment of Proxima b flyby takes 4.2 years to reach Earth. A response, if Earth could transmit one immediately upon receipt, would take another 4.2 years to arrive at the spacecraft's location, by which point the Starship has traveled approximately another 8.5 light-years beyond its original position. The round-trip communication time is 8.4 years. The spacecraft has long since passed through the Proxima Centauri system and is receding into interstellar space at 20% of light speed by the time Earth even learns the flyby has occurred. There is no mission control in any meaningful real-time sense. There is no team of engineers watching telemetry and making decisions. There is no capacity to respond to unexpected discoveries, to redirect the spacecraft toward an anomalous feature, to extend an observation sequence when something interesting appears in the data. The Starship executes its mission entirely alone. The commands it carries were written years or decades before it reaches its destination by engineers who could not know what it would find when it arrived. The decision trees embedded in its software, if the atmosphere shows this signature, allocate this many spectrometer exposures. If the planet's reflectance pattern suggests this, prioritize. These imaging wavelengths represent the best prediction that a team of humans, separated from the encounter by 24 years and 4.2 light-years, could make about what would be scientifically valuable to observe. This is not unprecedented in space exploration. The New Horizons spacecraft conducted its Pluto flyby in a fully autonomous mode because the round-trip communication time to Pluto is approximately 9 hours too long for real-time control during a high-speed encounter. The observation sequences were programmed months in advance and executed without human oversight during the critical encounter hours. But New Horizons' autonomous operation lasted hours. A Starship's autonomous operation lasts 20 years. The software written for a Starship must anticipate not just the specific encounter with Proxima b, but every eventuality that might arise during 2 decades of interstellar cruise. Hardware failures must be handled autonomously. The system must detect when a component has degraded, adapt its operation to compensate, and continue the mission without any possibility of receiving guidance from Earth. Navigation corrections must be calculated on board, using star tracker data, without the luxury of Earth-based ranging and orbit determination that has underpinned every planetary mission we have ever flown. The onboard artificial intelligence, minimal as it must be given the mass constraints, must be sophisticated enough to make scientifically meaningful decisions during the flyby without any human involvement. It must recognize when it has found something unexpected and allocate observing time appropriately, balancing the competing demands of multiple instruments against the hard constraint of a closing observation window. Writing this software is arguably as difficult as building the hardware. It requires specifying in advance how an autonomous system should behave in situations its designers cannot fully anticipate. It requires encoding not just rules but judgment, the capacity to weigh competing priorities against each other in real time, to recognize that a cloud feature developing rapidly on the day side of Proxima b is scientifically more valuable in this moment then a seventh image of the night side's thermal emission. This is the kind of problem that sits at the boundary between aerospace engineering and artificial intelligence, and it has no fully satisfying solution. The best any design team can do is make the system as adaptable as possible within the mass budget, test it extensively against simulated scenarios, and then release it into the universe with the knowledge that its performance during the 4 most important minutes of the mission will be entirely outside human control. When the data finally arrives, it will enter a world that has been transformed by 24 years of change. The scientists who receive the first transmissions from a starship at Proxima Centauri will not in most cases be the same people who designed and launched the mission. They will be the generation that came after students who were graduate students or undergraduates when the launches occurred, or researchers who entered the field in the intervening years, attracted partly by the existence of this mission progress, by the knowledge that somewhere in the interstellar dark, a message was traveling toward them that would arrive during their careers. This is one of the stranger psychological aspects of interstellar exploration. The knowledge that data is coming that right now in this very moment as you read these words. If such a mission had been launched years ago, photons are traveling toward Earth. Carrying information about another world creates a relationship between the present and the future, unlike anything else. Ordinary scientific practice. Experiments in physics or chemistry or biology produce results in seconds or hours or years. The researcher who designs an experiment typically lives to see its outcome. The emotional arc of curiosity, effort, uncertainty, and resolution that constitutes scientific practice operates on human timescales. The experimenter and the result inhabit the same moment in time. Interstellar science does not work this way. The people who will receive Proxima b flyby data will inherit it. They will analyze images taken by a machine that was launched before many of them were born, executing code written by engineers who are now old or gone, of a world that no human has ever seen, except as an inferred wobble in a distant star's radial velocity. They will spend their careers preparing for this inheritance, developing the signal processing techniques to extract the data from noise, building and maintaining the receiving arrays that will collect the transmission, writing and rewriting the analysis software that will turn raw photon counts into calibrated spectra and images, educating themselves about Proxima b's properties based on 24 years of additional telescope observations, theoretical modeling, and informed speculation. And then one day the first bits will arrive, and all of that preparation will meet its purpose. The emotional experience of this moment is difficult to imagine from our current vantage. We have no precedent for it. Every major discovery in the history of astronomy, the moons of Jupiter, the spiral structure of galaxies, the cosmic microwave background, the first exoplanet detection, was made in something close to real time. The astronomer looked at the data and saw the thing. The discovery and the discoverer were contemporaneous. Proxima b flyby data will arrive with a 24-year delay built into its physics. The discovery and the moment of observation will be separated by nearly a quarter century. The images will show a world as it was 24 years ago, as it was when the starship flew through its system, not as it is in the moment the data arrives. In a philosophical sense, the scientists examining those images will be looking at the past in a way that is more literal than the usual observation that all astronomical data represents the past. This past will be specific, dated. The world in those images will be as it was on a specific day and hour, calculable from the mission timeline in a year that the scientists receiving the data will remember from their own lives. They will know, examining those images, what was happening on Earth on the day those photons left Proxima b's atmosphere and were captured by a gram-scale camera 4 light-years away. They will be able to say, on this date, 24 years ago, while this was happening on our world, a machine we built was passing within 50,000 kilometers of another planet and taking these photographs. The simultaneity of human history and cosmic exploration, usually separated by the abstraction of light years and centuries, will be made intimate in a way it has never been before. There is another dimension to the communication delay that carries its own specific weight. When the starship transmits its data, it does so without knowing whether anyone is listening. The spacecraft has no way to confirm that Earth's receiving arrays are operational and pointed in the right direction. It cannot send a handshake signal and wait for acknowledgement before transmitting the full dataset. It simply begins transmitting according to its pre-programmed schedule, trusting, if a machine can be said to trust anything, that the civilization that built and launched it has maintained the infrastructure to receive the transmission over the 4 years it takes to arrive. This requires an institutional continuity that is not guaranteed. 24 years is long enough for significant changes in national priorities, funding structures, and scientific leadership. Space programs have been defunded, restructured, and redirected over shorter intervals. The engineers who built the receiving arrays and wrote the data processing software will have retired or died. The institutions that funded them may have evolved beyond recognition. The political coalitions that supported the mission may have dissolved and reformed around different priorities. Maintaining active listening infrastructure for 24 years, specifically maintaining it in the knowledge that the transmission will arrive at a precisely calculable time, making it possible to focus resources in a narrow window, is more tractable than maintaining passive listening indefinitely. The mission timeline gives future scientists. This is both a pressure and a gift. The pressure is obvious. The gift is this: it creates a purpose that extends across generations, a reason for young scientists entering the field in the years between launch and data arrival to care about Proxima b, to develop expertise in red dwarf planetary science, to build the analytical tools that will be needed when the images arrive. The mission in transit is not a passive waiting. It is an active preparation, a decades-long invitation to the scientific community to be ready for something extraordinary. Every generation of astronomers studying Proxima b with Earth-based or space-based telescopes in the years between launch and data return will be, in a sense, writing the context for the data that is coming. Every theoretical model of tidally locked atmospheres, every observation of Proxima Centauri's flare activity, every constraint on Proxima b's mass and orbital parameters, all of it accumulates into a framework that will allow the flyby data to be interpreted with maximum scientific value when it finally arrives. The mission is not a single moment. It is a 24-year scientific conversation in which one side speaks first and waits a very long time for the reply. Beneath all of this, beneath the engineering and the physics and the institutional challenges and the philosophical strangeness of communicating across light years and decades, there is a question that does not have a clean scientific answer. Why does it matter? Not in the instrumental sense of advancing our knowledge of planetary science, or exoplanet atmospheres, or astrobiology. These justifications are real and important, and would alone be sufficient to motivate the mission in a rational accounting of scientific priorities. But they are not the reason this particular mission captures something deeper than ordinary scientific curiosity. They are not why the discovery of Proxima b produced headlines in publications that rarely cover planetary science. They are not why breakthrough starshot attracted attention from people with no professional interest in aerospace engineering or photonics or semiconductor fabrication. The reason is simpler and less rational and more true. We want to know if we are alone. This question has no precise scientific formulation. It is not a hypothesis that can be tested with a single observation or a series of measurements. Even if a starship flies through the Proxima Centauri system and detects oxygen and methane in Proxima b's atmosphere simultaneously, the strongest possible biosignature a brief flyby could detect, it would not prove life. It would make life by far the most parsimonious explanation. It would shift the probability distribution dramatically. It would be in any reasonable interpretation the most important scientific discovery in human history. But it would not be proof, not in the sense that satisfies the most rigorous standards of scientific inference, and yet the question would feel answered in the way that matters to beings who evolved asking it. Because the question is not really about Proxima b specifically, or about the chemistry of its atmosphere, or about the evolutionary pathways that might or might not have produced biology on a tidally locked world around a flare star 4 light-years away. The question is about the universe itself, about whether the process that produced conscious, curious, self-aware life on this particular rocky planet around this particular average star in this particular undistinguished corner of one galaxy among 2 trillion, Whether that process is a cosmic accident that happened once or a cosmic tendency that happens everywhere, conditions allow. If it happened twice in the nearest few light years, it has almost certainly happened billions of times throughout the galaxy. If it happened only once in 4 billion years on this single world, then we are something stranger and more isolated and more precious than we have any framework to fully comprehend. Either answer transforms how we understand what we are. Either answer is worth 20 years of travel and 4 light years of silence and decades of patient preparation and a gram of silicon and metal flying through the dark at 20% of the speed of light. Either answer is worth reaching for. Carl Sagan wrote in the last years of his life that our planet is a lonely speck in the great enveloping cosmic dark. He wrote this not as despair, but as instruction, as an invitation to look at the pale blue dot photograph taken by Voyager 1 from beyond the orbit of Neptune, and understand viscerally and permanently what it means to be here, what it means to be the kind of creature that builds telescopes and launches spacecraft and asks questions whose answers it may never live to receive. Sagan understood something that the engineers and the physicists and the mission planners sometimes lose sight of in the necessary granularity of their work. The point was never simply to go. The point was to become the kind of species capable of going. The journey to the stars is not primarily a technological problem. It is a civilizational one. And civilizations, unlike spacecraft, cannot be optimized in a laboratory or tested in a vacuum chamber. They are built from choices, accumulated across generations about what matters and what does not, about what is worth the cost and what is not, about whether the universe beyond our atmosphere deserves our attention or whether our attention is better spent entirely on the urgent and the immediate and the close. We are not at present that civilization. We are a civilization that struggles to maintain funding for scientific programs across the span of a single political administration. We are a civilization that abandoned the moon after 6 visits and has not returned with human beings in more than half a century. We are a civilization that conceived the International Space Station as an experiment in international cooperation and then allowed it to become a symbol of political ambiguity, its future perpetually uncertain, its scientific return consistently underfunded relative to its operational costs. We are a civilization that knows with mathematical certainty that the nearest potentially habitable world is 4.2 light-years away, and has so far committed $100 million, roughly the cost of a moderately successful Hollywood film, to the question of how we might reach it. This is not a criticism, it is an honest accounting of where we are. And where we are is not the end of the story. It is almost certainly the beginning of it. The Fermi paradox sits at the edge of every serious conversation about interstellar travel, a shadow that falls across the optimism of laser arrays and gram-scale spacecraft, and 21-year transit times. In the summer of 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos, the same institution where Orion would be born 9 years later, when the conversation turned to the possibility of extraterrestrial intelligence. Fermi listened to the speculation about other civilizations and advanced technology and interstellar travel, and then asked a question that has not been satisfactorily answered in the 75 years since. Where is everybody? The Milky Way galaxy is approximately 13.6 billion years old. It contains somewhere between 200 and 400 billion stars. The fraction of those stars hosting rocky planets in habitable zones, as revealed by the Kepler mission and its successors, is substantial, perhaps 20 to 30% of Sun-like stars, and possibly higher fractions of the more numerous red dwarfs host planets in potentially habitable configuration. Even the most conservative estimates yield billions of potentially habitable worlds in our galaxy alone. If even a tiny fraction of those worlds produce technological civilizations, and if even a tiny fraction of those civilizations develop interstellar travel capability, the galaxy should be, by straightforward calculation, teeming with evidence of intelligent life, signals, artifacts, megastructures, the signatures of industrial activity visible across light years. Something. We have found nothing. The silence is not from lack of looking. The SETI Institute and its predecessors have been listening to radio frequencies from thousands of stellar targets for decades. The Breakthrough Listen program, associated with the same Yuri Milner who funds Breakthrough Starshot, uses major radio telescope facilities to survey millions of stars across broad frequency ranges. Optical SETI programs search for laser pulses that might carry interstellar communications. Each year, the sensitivity of these searches improves. Each year, the portion of plausible signal space they can exclude grows larger. And each year, the silence continues. The Fermi paradox is at its core an argument about the difficulty of interstellar travel. One resolution to the paradox, perhaps the most sobering one, is that interstellar travel is so difficult that no civilization achieves it within the lifespan of the galaxy. That the distances are simply too great, the energy requirements too formidable, the timescales too long for any civilization built from biological creatures with finite lifespans and finite patience and finite institutional continuity to bridge. That the stars are each alone not by accident but by design. That the universe is structured at the most fundamental level of its physics, to keep its islands of matter and mind and complexity permanently isolated from one another. If this is true and we cannot yet rule it out, then the silence we hear is not the silence of an empty universe. It is the silence of a universe full of civilizations that tried and failed, or tried and gave up, or never tried at all. A universe in which the question, where is everybody, has the answer right. Where they started, unable to bridge the gap, looking up at the same dark sky we look at, asking the same question we ask. There is another resolution, less dark and perhaps more instructive. Perhaps the civilizations are there. Perhaps some of them have attempted interstellar missions, robotic probes, laser-pushed sails, nuclear pulse vehicles, and those probes are crossing the dark right now, years or centuries from their destinations, too small and too cold, detect with our current instruments. Perhaps the silence is not absence but invisibility. Perhaps we have not yet built the instruments sensitive enough to see what is already crossing the void. Perhaps the first signal we receive from another civilization will not be a radio broadcast aimed at us from a planetary transmitter. Perhaps it will be one ordinary day the detection of an anomalous object crossing through our solar system, something small, something artificial in its geometry, something that carries in its structure the unmistakable signature of deliberate manufacture. We would not know what to do with that. We have no protocol for it. We have no institutional framework for interpreting it. We have as a civilization spent remarkably little time preparing for the scenario in which the universe answers our question. This is in itself a measure of where we are. A civilization that has not yet seriously prepared for the possibility of contact is a civilization that has not yet fully internalized what it means to live in a universe this old and this large. The preparation for contact, the scientific, philosophical, and social preparation, is part of the same maturation process that interstellar exploration requires. You cannot reach the stars without first becoming a civilization that takes the stars seriously. What does it mean to take the stars seriously? It means funding Breakthrough Starshot not at the level of a moderately successful film, but at the level of a national infrastructure project. It means building the laser arrays and the receiving stations and the starship fabrication facilities with the same commitment that earlier generations built railroads and highways, and the internet, understanding that the infrastructure, itself independent of any specific mission, creates capabilities and possibilities that cannot be anticipated in advance. It means educating a generation of scientists and engineers who understand that their most important work will produce results they may not live to see, and who choose to do that work anyway, who plant trees in whose shade they will never sit, who lay foundations for buildings whose spires will be completed by their grandchildren. It means developing the institutional structures, the international agreements, the long-term funding mechanisms, the scientific consortia capable of maintaining focus and continuity across decades and generations. The kind of institutions that have sustained other multi-generational projects. The network of particle accelerators that has been expanding and refining our understanding of fundamental physics for 70 years. the astronomical observatories that have maintained continuous sky surveys across multiple generations of astronomers, the mathematical research programs that have pursued problems requiring centuries to solve. It means most fundamentally making a collective decision that the question of whether we are alone in the universe is worth answering, not as a curiosity, not as a philosophical diversion, as the central question of our civilizational project, the question that more than any other determines what kind of universe we inhabit, and therefore what kind of civilization it is meaningful to build. A universe teeming with life is a different kind of universe than an empty one. A universe in which intelligence arises easily and spreads widely is a different context for human existence than a universe in which we are the only minds in 2 trillion galaxies. The answer changes everything, not in a way that can be immediately operationalized, not in a way that alters the physics of our daily lives, but in the way that understanding your place in a larger context always changes how you inhabit that place. We have been asking this question in various forms for as long as we have been capable of asking questions. Every culture that has looked at the night sky and wondered about the points of light has constructed an answer of some kind: mythological, theological, philosophical, scientific. The answers have always reflected what we were capable of imagining at the time. We are now, for the first time in the history of this question, capable of imagining an answer that is testable, that can be pursued with hardware and lasers and mathematics. That will arrive if we pursue it with sufficient seriousness and sufficient patience as data. Actual data. Photons carrying information from another world collected by an instrument we built, transmitted across 4 light-years of void, to receiving dishes we constructed and aimed at the right piece of sky. This is not mythology. It is not theology. It is not philosophical speculation. It is science. It is engineering. It is the accumulated product of every generation of curious human beings who looked up and refused to stop asking. And so we arrive at last at the place where the physics and the philosophy converge: 4.2 light-years. 40 trillion kilometers of absolute darkness, broken only by the occasional hydrogen atom drifting alone through a void, so perfect it has no analogue on Earth. At the far end of this darkness, a dim red star. Around that star, a world, rocky probably, tidally locked almost certainly, irradiated by stellar flares more powerful than anything our sun produces, possessing an atmosphere or not, harboring chemistry of interest or not, harboring something stranger and more wonderful than chemistry or not. We do not know. We cannot know from here with what we currently have. But we know where it is. We know its orbit and its mass and its distance from its star. We know the physics that governs the light that could push a sail toward it. We know the mathematics that determines what a starship would need to weigh, and how large its sail would need to be, and how powerful the laser array would need to be. We know with a specificity and rigor that would have seemed impossible to astronomers even 50 years ago, what it would take to send something of ours across that darkness. The knowing is itself a kind of miracle. Not in any supernatural sense, but in the sense that deserves genuine awe. 4 billion years of biological evolution, 10,000 years of accumulated human culture and knowledge and technological development, a few hundred years of modern science, a few decades of space exploration and exoplanet detection, laser physics, and the result is a species that can look at a dim star, invisible to the naked eye, and say, there is a world there, and here is how we might reach it. We are made of the same material as that star. The carbon in your body was forged in stellar interiors. The oxygen you breathe was created in supernova explosions. The iron in your blood was scattered across the galaxy by dying stars billions of years before our sun formed. The atoms that constitute you have traveled over the age of the universe, distances that make 4 light-years seem intimate. You are in the most literal physical sense, a piece of the cosmos that has become aware of itself, a fragment of the universe that has developed the capacity to wonder about the rest of the universe. The atoms that once drifted through the interstellar medium, indifferent and dark and cold, have assembled themselves into something that builds laser arrays and writes equations and asks whether other such assemblages exist around stars. This is not poetic license. This is chemistry and physics and evolutionary biology arriving at a conclusion that feels, despite its rigorous scientific basis, like something close to wonder. Whether we reach Proxima b in 20 years or 50 or 200, whether the first star chip to arrive there transmits images of a living world or a barren one, whether Breakthrough Starshot succeeds in its current form or evolves in something its founders could not have imagined, none of this changes what the attempt itself means. The attempt means that we are a species that does not accept the horizon as a final boundary, that the gulf between stars, however vast, however hostile, however indifferent to our ambitions, does not constitute a permanent limit on what we will try to reach, that the 4 light-years separating us from Proxima b are not in the final accounting a wall, they are a distance, and distances given sufficient time and sufficient ingenuity and sufficient refusal to stop trying can be crossed. Every civilization faces a moment when it must decide what kind of civilization it wants to be, whether it turns inward, consumed by its own complexity and its immediate needs and the 1,000 urgent problems that crowd out the important ones, or whether it maintains alongside all the urgent, the long vision, the ability to pursue goals whose rewards accrue to generations not yet born. We are at that moment. The laser arrays are not built yet. The star chips are not fabricated yet. The mathematics is solved and the physics is sound, and the engineering pathways are understood in their broad outlines, but the hardware does not yet exist, and the funding is not yet committed, and the institutional structures are not yet established. The dream is real. The capability is not yet. What happens next depends on choices, on whether we decide as a civilization that the question of Proxima b is worth answering, that the cost in funding and time and engineering effort and the long patience required of multi-generational projects is justified by the magnitude of the answer. It is. Not because the scientific knowledge is uniquely valuable, though it is, not because the technological spin-offs of laser array development and nanofabrication and interstellar communication research would benefit society, though they would, but because the decision to try, the decision to look at 40 trillion kilometers of darkness and say, not someday perhaps, but here is how and here is when and here is what we will build, is itself the thing. It is the civilization becoming what it needs to become. It is the species growing into the universe it inhabits. The stars have been there for billions of years. They will be there long after we are gone, whether we reach them or not. They do not need us to reach them. They are not waiting, but we need to reach for them. Not for what we will find at the destination, though what we find may be the most important discovery in our history, for what we become in the reaching, for the kind of thinking and the kind of cooperation and the kind of long-sighted, patient, humble ambition that the attempt requires and that once developed for this purpose will serve us in every other challenge we face. The universe is not hostile to us. It is simply vast and old and operating on scales that make our current capabilities look from a certain perspective almost comically limited. But it is also the universe that produced us, that assembled from hydrogen and time and the slow accumulation of complexity creatures capable of calculating the distance to other stars and designing the machines that might one day cross it. The capability to ask the question carries somewhere within it the seed of the capability to answer it. We are right now in the long gap between the asking and the answering, and the asking was already miraculous. Somewhere in the southern sky, invisible without a telescope, a red star burns. It has been burning for 4.8 billion years, and it will continue burning for another 4 trillion longer than the current age of the universe, by a factor of nearly 300. Around it, a world turns its locked face toward the perpetual light and its other face toward the permanent dark, and the terminator between them stretches across the surface in an eternal twilight that has persisted unchanged since before our sun formed. No one has ever seen that world directly. No instrument of human origin has ever gathered light from its atmosphere or measured the composition of whatever gas, if any, surrounds it. It exists in our knowledge as a wobble in a stellar spectrum, as a statistical inference from careful observation, as a probability distribution over mass and orbital parameters. It waits 4.2 light-years away in the absolute silence of interstellar space, indifferent to whether we ever come. But we know it is there, and somewhere in a laboratory, in a university, in a conference room, where engineers are arguing over sail materials and laser frequencies and chip fabrication processes and signal processing algorithms somewhere in the accumulated human effort directed at the problem of crossing that distance. A small step is being taken, a calculation is being refined, a material is being tested, a design is being improved. The light that will one day push a sail toward that world has not yet been generated. The sail that will catch it has not yet been made. The chip that will open its camera and see Proxima B for the first time has not yet been fabricated. But the mathematics that describes how it will work is already written. The physics that makes it possible has always been true. The question that motivates the entire endeavor has been burning in the human mind since the first night. The first conscious creature looked up at the stars and felt the weight of the darkness and the pull of the light, and understood in whatever language was available to it that the universe is larger than this moment, this place, this single small world. We are that creature grown older and more capable and still asking. The darkness between the stars is not empty. It is full of light we have not yet sent. The distance to Proxima B is not a wall. It is an invitation. And somewhere in some laboratory, in some graduate student's calculations scrawled on paper at 2 in the morning, in some engineer's quiet certainty that the problem is solvable, the answer to that invitation is being written, one photon at a time. One calculation at a time, one generation at a time, reaching always toward the light.